So in this video, we're going to give an overview of circuit components that actually serve as sources. So particularly the idea of a voltage and current source. So when we talk about an actual circuit element, we gave kind of the schematic diagram in one of the prior slides, and we said that all that we're going to care about is how it acts from an interface point of view. We're actually going to abstract away what's going on the inside. And now that we have the definition of voltage and current from the prior slides, we can basically just reason about that one way to describe the terminal behavior is when we connect a voltage across it, what kind of current is actually drawn. So that is known as an IV relationship, or current and voltage relationship. So that will actually serve to be the modeling bins of the circuit components that we use in circuit analysis. For example, if when we have a voltage or a push, if we keep increasing that push and the current increases in a linear fashion, that IV relationship would be a linear function. And we will call anything that obeys a linear function in terms of its IV relationship to be a resistor from a modeling point of view. So that's how we're actually going about doing the modeling. What we'll see majorly in this class is the IV relationships are either algebraic in the form of a resistor, or they can be differential equations in terms of components that store energy, like reactive components. So this, I'm going to edit it real quick. That should be independent. So when we talk about these sources here, we're going to talk about independent and ideal. So let's talk about what both of these mean. Well, if a voltage source, and remember that a voltage source is just going to provide a push relative of one terminal to another, and we're going to need some indication of polarity at which of the terminals is at high potential and which is at low potential. If it provides a common push, say 10 volts, independent of whatever load is connected across it, that is referred to be an independent source. So your book actually refers to it as it produces the same voltage value independent of the current through it, because they haven't talked about Ohm's law yet, but what we're going to see is that the current through it turns out to be directly related to the load. So the reason that that's called an ideal source, in addition to being independent, is that if you think about power being described as the product of current and voltage, if that ideal voltage source will hold that voltage for any current value, the current can become infinite, and then in that case, power would be infinite, and that is not possible, right? So it is an ideal source. In terms of the schematic models used to describe the various ideal and independent voltage sources, you see there's quite a bit of them. All of them have the common notion of having polarity indicated, plus and minus. Here on the left, we call this an ideal DC source. This is also a DC source in the middle, but it's usually reserved for modeling actually components that are batteries. And here on the right, we have an AC source, and that is indicated by the sinusoidal waveform in between the two polarity marks of plus and minus. So what is an ideal independent current source? Well, it's just going to be a component or a source that's going to be capable of producing a fixed value of current regardless of what the level of voltage across it is. And that level of voltage, as we'll see once we get to Ohm's law, is going to be set based upon the actual load that we connect across. So again, the reason that it has to be ideal is if it's going to be say, for example, 2 amps, regardless of what this voltage value is, the way the current source works in an ideal sense is if you connect a load across it, it will generate whatever push it needs to drive that current through. So if you put an infinite load on it, right? In an ideal current source, you could generate enough push to drive that current through. That would be kind of asymptotically approaching infinite power consumption, which is not possible, which is why this is actually called ideal. So both of those were dependent sources because their value was just really set. It didn't depend on the value of the current through them, nor any other value of a circuit quantity anywhere else in the circuit. So dependent sources are just going to be controlled, their level, by some other physical factor, either voltage or current, measured elsewhere in the circuit. So when you think about why dependent sources are valuable, it's really just from a modeling point of view. And most notably, when you move on to your electronic devices class and you're using dependent sources to model the behavior of transistors, that's likely where you'll see these again. So the way that you can tell something quickly as a dependent source is if it's represented by this diamond as a schematic versus the circles that were used for the case of independent sources. If you notice here, there's a lot of different examples of dependent sources that are presented in your book. And really what they're differentiated by is A, whether or not they're a voltage, these are the two bottom, or a current source. And in addition, whether or not the scaling factor is just a scaling factor or whether it's controlled by something else. And here's what I mean by that. If you focus down here, if you notice the value that's actually controlling this voltage is a current. So you would call this a current controlled voltage source. And in order to get units of volts, if this is a current in amps, the units of this proportionality constant are going to have to be volts per amp to cause the amps to cancel. So this is a current controlled, in the lower right, voltage source, voltage controlled voltage source, current controlled current source, voltage controlled current source. And in each case, the units of the constant of proportionality will be whatever you need in order to get the value that you want. So in the case of a current source, it has to be in amps. So if it's current controlled, this is just a multiple. You can't change the units. Versus here, this is a current source. It has to be in amps. But the controller, it's voltage controlled. So you have to cancel out the volts. So the multiplier is in amps per volt and so on. So just as an example problem here, we have a relatively simplistic schematic. We're told that V2 is the voltage measured across this box. We have, if you notice here, a dependent voltage source. It is a voltage-dependent voltage source. And what we're basically asked to do is to find VL if we know V2 is 3. So let's go through the logic of how we would actually determine, and this is going to cause you to have to think back to your physics class a little bit because they're assuming that you actually know that when two components are connected in parallel, that their voltage is the same. So this is just the schematic that they give us redrawn. We know that V2 is 3 volts. That's the potential across this component. We want to find VL. Well, how do we do it? Well, we notice that the potential from here to here, which is VL, is the same as the potential across the dependent source from here to here because they're wired in parallel. So VL is equal to 5V2. That's all that I've written here. So if we know that V2 is 3 volts, 5 times 3 will just be 15 volts. So usually dependent sources problems at the beginning of the book are pretty easy. It's just about spotting the difference in the schematics and understanding whether they're voltage controlled or current controlled and the underlying meaning of the multiples.